What if the most consequential medical discovery of the 20th century began with a contaminated petri dish that most scientists would have thrown away? Before 1928, a simple wound infection could end a life that surgery had saved. Tonight, I am here with Rowan Hartsteele.
Good evening, Clara.
The central tension of this episode is the distance between a laboratory observation and a medicine that reaches a patient. Tonight, we turn to Alexander Fleming, a Scottish physician whose moment of attention in a London laboratory set in motion one of the most significant transformations in the history of human health. We ask what it means to discover something, and whether the person who first sees it deserves the full weight of the credit.
Fleming saw something that others had seen and dismissed. What made the difference was not luck alone, but the trained instinct to pause where another researcher would have moved on.
We are speaking about the discovery of penicillin and the antibiotic revolution it produced.
A revolution that required not one scientist but several, not one institution but many, and not one decade but two, before it reached the patients who needed it most.
Then let us begin with the world of medicine that Fleming entered and the problem that defined it.
At the beginning of the 20th century, bacteriology was a relatively young discipline. Scientists had established by then that many diseases were caused by specific microorganisms, and the work of figures like Louis Pasteur and Robert Koch had given medicine a new framework for understanding infection. But understanding the cause of infection and being able to treat it were two very different things. Before the development of antibiotics, a physician facing a bacterial infection had almost no effective tools. The options were supportive care, surgical drainage in certain cases, and waiting.
Zoomedicine could identify the problem, but could not intervene at the level of the bacterium itself.
Exactly. There was one partial exception, which was the work of Paul Ehrlich, a German physician who developed a compound called salvarsan in 1910, effective against the bacterium responsible for syphilis. This was the first example of what Ehrlich called a magic bullet, a chemical that could target a specific pathogen without destroying the patient. But salvarsan was highly toxic, difficult to administer, and effective only against a narrow range of infections. The broader problem of bacterial disease remained essentially unsolved. Wound infections, pneumonia, blood poisoning, childbed fever, these were still major causes of death throughout the early decades of the century.
So Fleming entered medicine during a period when the gap between diagnosis and treatment was enormous.
Yes, and his wartime experience deepened that awareness. Fleming served in the First World War as part of a military research unit studying wound infections. He watched men survive surgery only to succumb to infection in the days that followed. He became particularly interested in the limitations of antiseptics, which were the standard treatment at the time. Fleming demonstrated through careful experimentation that many antiseptics, far from helping, actually damaged the body's own immune defenses without reliably eliminating the bacteria they were meant to destroy.
So he arrived at his later discovery already convinced that the existing approach was flawed.
Exactly, and that conviction shaped how he looked at his laboratory work in the years that followed. He was not simply performing routine experiments. He was actively searching for something that could kill bacteria without harming the patient, an idea that was not widely shared at the time. By the late 1920s, Fleming was working at St. Mary's Hospital in London, running a bacteriology laboratory, and pursuing research on natural antibacterial substances. He had already made one significant early discovery, lysozyme, an enzyme present in tears and saliva that could destroy certain bacteria.
So, the discovery of penicillin was not his first encounter with natural antibacterial properties.
No, and this is the part that tends to be misunderstood. Fleming was not a passive observer who stumbled into a breakthrough by accident. He was an active researcher who had been thinking carefully about the relationship between biological substances and bacterial growth for years. The story of accidental discovery is real, but it is incomplete. What happened in September of 1928 was that Fleming returned to his laboratory after a summer holiday and noticed that one of his bacterial culture plates had been contaminated by a mold.
And most researchers would have discarded a contaminated plate.
Yes, but here is where it shifted. Fleming noticed something specific about this plate. Around the mold, the bacterial colonies had been destroyed. There was a clear zone where the bacteria had not grown, as if something produced by the mold was lethal to them. He recognized the significance of that observation immediately, because he had the conceptual framework to interpret it. Another researcher without his background in antibacterial substances might have seen only a failed experiment. Fleming saw a phenomenon worth investigating.
So, the accident was the contamination. The discovery was the decision to look more closely.
Exact. Fleming identified the mold as a species of Penicillium, and he named the antibacterial substance it produced penicillin. He then conducted a series of experiments showing that penicillin was effective against a wide range of bacteria, and crucially, that it was not toxic to animal tissue. He published his findings in 1929 in the British Journal of Experimental Pathology. The paper was careful and accurate. It described what he had observed and what he had tested, but it did not present penicillin as a ready medicine. Fleming himself was uncertain whether it could be purified and concentrated to a level that would make it clinically useful.
So the published discovery sat relatively unnoticed for over a decade.
Yes. This is one of the more striking facts about the history of penicillin. Fleming's 1929 paper received limited attention at the time. The scientific community did not immediately recognize its significance, in part because the technical challenge of extracting and stabilizing penicillin seemed, to most chemists, formidable. Fleming himself lacked the chemical expertise to purify the substance, and his attempts to collaborate with chemists who might help him were largely unsuccessful. Penicillin remained a laboratory curiosity, occasionally used in controlled settings but not pursued as a priority.
So the gap between observation and medicine remained open for more than 10 years.
Yes. And what finally closed it was a combination of institutional ambition, scientific collaboration, and the urgency of a Second World War. In the late 1930s, a team at Oxford University led by Howard Florey, an Australian pathologist, and Ernst Chain, a German biochemist who had fled Nazi Germany, began a systematic review of antibacterial substances. They encountered Fleming's paper, recognized its potential, and decided to pursue penicillin with the full resources of their laboratory. Chain developed the chemical methods needed to extract and purify penicillin in a stable form. By 1940, they had enough to conduct the first animal trials.
So Florey and Chain solved the problem that Fleming could not.
Yes, the animal trials were remarkable. Mice infected with lethal doses of bacteria survived when treated with penicillin. The results were so compelling that Florey moved quickly to human trials despite having only tiny quantities of the substance available. The first human patient to receive penicillin was a policeman in Oxford named Albert Alexander, who had developed a severe infection following a minor scratch. He showed dramatic improvement after treatment, but the supply of penicillin was so limited that the team was forced to recover and reuse the substance from his urine. When the supply was finally exhausted, his condition deteriorated and his life ended.
So the first clinical proof that penicillin worked also demonstrated the problem that would define the next phase of its history.
Exactly. The medicine worked, but it could not yet be produced in quantities sufficient to save lives at scale. This is the turning point at which the story of penicillin moves from laboratory science to industrial production. Florey traveled to the United States in 1941 to seek support for large-scale production. The timing coincided with America's entry into the war, following the attack on Pearl Harbor, and the military urgency producing a medicine that could prevent soldiers from succumbing to infected wounds became a national priority.
So the war created the conditions for scaling something that peacetime research alone might not have moved quickly enough.
Yes, American pharmaceutical companies, working with government funding and military contracts, developed industrial fermentation processes capable of producing penicillin in quantities that would have been unimaginable 2 years earlier. By the time of the Normandy landings in 1944, penicillin was available in sufficient supply to treat casualties. The contrast with the First World War was striking. Men who might have lost limbs or their lives to wound infections in the earlier conflict were treated and recovered. The proportion of soldiers who passed away from infection dropped sharply. Military medicine had crossed a threshold.
So penicillin did not simply change civilian medicine. It changed the experience of war itself.
Yes, and after the war, the infrastructure built for military production was redirected to civilian supply. Penicillin became widely available in hospitals throughout the late 1940s, and eventually in many countries accessible to ordinary patients without hospitalization. The effect on public health was profound. Diseases that had routinely ended lives, scarlet fever, rheumatic fever, bacterial pneumonia, syphilis, were brought under clinical control within a single decade. The expectation of what medicine could do shifted fundamentally.
So patients began to expect that infections would be treated and resolved, rather than simply endured.
Exactly. And this shift in expectation is perhaps as significant as the clinical reality. The antibiotic era produced a transformation not only in what medicine could achieve, but in how patients, physicians and governments understood the relationship between science and health. In 1945, the attribution acknowledged what the history of the discovery actually showed, that no single person was responsible, and that the path from observation to medicine required contributions that no one individual could have made alone.
Before we close tonight, let us take a brief pause and welcome Margaret Evernight. Margaret, for those who want to understand how penicillin moved from Fleming's laboratory to the medicine that reshaped the modern world, where would you invite them to continue it?
Thank you, Clara. In this case, the most direct path is also the most important one. I would suggest beginning with The Mold in Dr. Florey's Coat by Eric Lax.
So this is a book that follows the full arc, from Fleming's observation through to the antibiotic revolution.
It is. Lax traces the development of penicillin from initial discovery to widespread medical use, giving particular attention to the roles of Florey and Chain alongside Fleming. He situates the antibiotic revolution within the context of scientific collaboration, institutional research, and wartime urgency.
And is this a book that requires prior scientific knowledge to follow?
It does not. Lax writes for a general reader with curiosity rather than expertise. The scientific processes are explained clearly without becoming technical, and the human stories behind the research, the personalities, the conflicts, the wartime pressures, are told with considerable care.
So reading, it gives you both the science and the people behind it in a way that holds together as a complete story.
Yeah, and it leaves the reader with a clear understanding of why no single name can carry the full weight of this discovery, which is itself an important lesson about how scientific progress actually works.
Thank you, Margaret. That is a thoughtful place to pause tonight.
Thank you, Clara. It was a pleasure.
The legacy of Fleming's discovery is layered in a way that reflects the complexity of how it came about. In the popular imagination, Fleming is the central figure, the Scottish scientist who noticed what others missed and gave the world a cure. That image is not false, but the historical record shows that Fleming himself understood the limitations of what he had contributed. He was generous in his public acknowledgments of Florey and Chain, and he repeatedly cautioned against the romanticization of his own role.
So, Fleming himself resisted the myth that grew around him.
In large part, yes. He was a private and understated man, and the celebrity that followed the Nobel Prize made him uncomfortable. He gave hundreds of public lectures and interviews in the final decade of his life, but his message was consistently one of caution. In particular, Fleming warned about the dangers of antibiotic resistance from an early point. In his Nobel Prize acceptance speech in 1945, he cautioned that using penicillin in insufficient doses would allow bacteria to develop tolerance, creating strains that the medicine could no longer reach.
So he anticipated, at the moment of the greatest triumph, the problem that would define the next century of antibiotic medicine.
Exact, and that warning went largely unheeded in the optimism of the post-war period. Antibiotics were prescribed widely, sometimes indiscriminately, in human medicine and later in veterinary and agricultural contexts. Resistant strains began to emerge within years of penicillin's widespread introduction. By the 1950s and 60s, penicillin-resistant strains of Staphylococcus aureus were already a recognized clinical problem in hospitals. The response was the development of new antibiotics, which in turn produced new resistant strains. The cycle that Fleming had warned about was already in motion.
So, the antibiotic revolution contained within it the conditions for its own limitation.
Yes, this is one of the more difficult aspects of the legacy. The discovery was genuine and the benefit was enormous, but the way the discovery was used, the speed, the volume, the breadth of application, created biological pressures that are now among the most serious challenges in global medicine. Antimicrobial resistance is now a recognized global health emergency. Certain bacterial infections that were once easily treated have become difficult or impossible to address with existing medicines. The pipeline of new antibiotics has slowed considerably because the economics of antibiotic development do not favor investment in the same way other pharmaceutical categories do.
So the world that penicillin created is now facing the possibility of losing what penicillin gave it.
That framing is accurate, and it gives the history of Fleming's discovery a particular kind of weight. The observation he made in 1928 set in motion not only a revolution, but a responsibility that the institutions and systems that followed him did not fully meet. Fleming's broader influence on medicine also includes what the antibiotic era revealed about the nature of scientific progress itself. The story of penicillin became a model for understanding how discovery, development, and deployment are distinct phases, each requiring different kinds of knowledge, collaboration, and resources.
So the lesson is not only about penicillin, it is about the structure of how science moves from insight to impact.
Yes, and that lesson continues to shape how research institutions, governments, and pharmaceutical companies approach the development of new medicines. The model built around penicillin, combining academic research, industrial production, and public health deployment, became the template for the pharmaceutical industry of the second half of the 20th century. Fleming passed away in 1955, a decade after the Nobel Prize and a quarter century after his original observation. In that time he had become one of the most recognized scientists in the world, celebrated in ways that few researchers ever experienced during their own lifetimes.
So he lived long enough to see what that contaminated plate had set in motion.
Yes, and long enough to understand that the work was far from finished. The question he left behind, how to use a powerful tool without destroying its effectiveness, remains one of the defining questions of medicine in the 21st century.
Thank you for staying with us tonight. And thank you, Rowan, for guiding us through the laboratory, the war, and the long shadow that Alexander Fleming's discovery continues to cast over modern medicine.
A contaminated plate that most would have discarded became the foundation that has extended more lives than perhaps any other single discovery in human history, and the responsibility that comes with that fact has not diminished with time.
If this conversation stayed with you, you are welcome to like, comment, and subscribe. You will find other episodes here where history, ideas, and power are approached slowly. Until next time, stay with us.